Okay, thank you, everyone. So I would like to take this opportunity to thank all of our speakers, Jing, Yanxun, and Yingqi, for sharing their wonderful talks and wonderful research. So especially Yingqi, I think even now it's still like just 6 o'clock in the morning. So that means Yingqi actually joined us about 5 o'clock in the morning. So before we head to the next section, the organizing committee of the conference asked us to take a group photo for all our speakers and also the next section speakers. So for those of you who are online, please turn on your camera. And so Wenjie, you are taking the picture, right? So when you take the
Yes,
picture,
Professor Wang. Yeah.
could you also count so we all know?
Okay. So 3, 2, 1, smiling. Okay. I have taken a shot. Yeah.
Do you need to take another one just in case?
Okay. I have taken several pictures. Yeah.
Okay. Thank you, everyone. And thanks for everyone for joining us from the audience as well. And I'm going to hand this to Robin.
Thanks very much. So the next section is going to be a little bit different. We're going to be talking about something called imsets. So we've got a great lineup of speakers today. So we're going to start with Milan Studený, who is going to give us a bit of an introductory talk, and then we'll have 3 talks that sort of follow on from that. So if you miss Milan's talk, you'll struggle a little bit because a lot of the definitions for the later talks will be given by Milan. Okay, are you ready, Milan, to start?
Yes.
Great. Do you want to share your screen?
Yes, I'm ready to start. Okay, full screen.
And just to say to all the speakers, I will give you a little nudge. There's 5 minutes left after 23 minutes, okay? So Milan Studený is a researcher at the Czech Academy of Sciences in Prague, and he's going to give us his introductory talk on imsets, in particular structural imsets that you can use for learning graphical models. So take it away whenever you're ready, Milan.
Okay, so I need to Control L. It's not working.
Maybe close the menu and click on the thing.
Úpravy zobrazení. Yes, try the menu zvětšení. Yes.
So I think if you close the menu, just click on the slide. Now try. Thanks.
So first, I would like thanks to Robin for organizing this event, this session, and for inviting me to participate in this. The title of my talk is on structural imsets for describing and learning graphical models. This is a summary. In the beginning, I would like to say a few words about the motivation of this approach. Then I will give the definitions. So in the beginning, I would like to talk about conditional independence concept, and then define formally the concept of structural imset and mention some of the basic results on this. Structural imsets are also related to supermodel functions, so I will also explain the relation to this. In the end of the talk, I would like to explain possible application in the context of learning graphical models, a kind of algebraic approach to learning graphical models. So this is the motivation. It is well known that the conditional independence concept is at the core of graphical statistical models. Actually, there are 2 possible approaches or interpretations to graphical models. Graphical models have their basic conditional independence interpretation, and on the top of that, there is an extended causal interpretation, which is at the topic of this conference, as I understand. Here is a reference to 2 books on this conditional independence interpretation of graphical models. The point is this: as the number of variables increases, and the graphs over any nodes cannot faithfully describe all possible condition independent structure induced by n discrete random variables. The reason is theoretical, because the number of graphs, say, grows exponentially with n, but number of condition independent structure grows super exponentially. So therefore, even different types of edges does not help. So this observation was motivation to develop a linear algebraic approach to describe condition independent structures using certain vectors whose components are integers. And these vectors can also be used to describe graphical models. So the vectors are called structural imsets. And the method of imsets gives a kind of sufficient condition for verifying the probabilistic implication between condition independent statements. And the respective inference mechanism is based on linear algebraic operations with imsets. And imsets can be utilized also in context of learning graphical models. They can be used as a linear algebraic representatives of equivalence classes of graphs. And finally, there is some connection of structural imsets to supermodular functions. Let me note in this context that supermodular function or their mirror images, supermodular functions, play quite important role in optimization theory. Here is a reference to Fujishige's monograph on this topic. So this page recalls the basic definition of condition independence, which is used in probabilistic reasoning. Let me recall the context we consider. N is a finite set of variables of interest, random variables or nodes of graphs. P of n, this symbol, denotes the power set of n. This is collection of all subsets of n. And I will use two notational conventions. To denote the union of two sets, I will simply skip the symbol of union and write just juxtaposition of the corresponding set symbols. And also, notation of a singleton will be simplified. I will skip the parentheses. Now, given pairwise disjoint subsets of n, NBC, and given a discrete probability distribution P over n, we said that A is conditionally independent of B given C with respect to P and use this notation. If conditional probability of A given BC actually does not depend on B, only depends on B through C, that means it equals to conditional probability of A given C. Formal definition is here. Any statement of this form will be called the condition independent statement. And the condition independence model induced by P is then collection of all these triplets of pairwise disjoint subsets of N, which represent valid condition independent statements with respect to P. This is one of possible definitions, but there are more advanced definitions which apply in wider contexts. For example, in statistics, we have more general situation with discrete, continuous probability distributions. So there is some framework which involves both the continuous statistical framework and the discrete computer science framework. So this is the framework of marginally continuous probability distributions. Marginally continuous distribution is a distribution on a joint sample space. This is multidimensional probability distribution where the components correspond to random variables. Where P is absolutely continuous with respect to some reference product measure, dominating product measure. In statistics, it is typically a Lebesgue measure on the respective Euclidean space. In computer science or artificial intelligence, is the counting measure. Then for any subset A of n, the marginal measure for A is described by its marginal densities, which is formally a function on the joint sample space, non-negative, but it depends only on factors in A. And so we have two equivalent definitions. This is one elegant, that A is independent of B given C, if and only if the marginal distribution for ABC times the distribution for C equals to the product of distribution for AC and BC. And equality, it's meant in a sense almost everywhere with respect to the dominating measure. There is even simpler equivalent condition. There's a factorization condition. Actually, that the marginal density for ABC can be written as product of two potentials. One of them depends on AC and one of BC on BC. Now we come to the definition of an imset. An imset is a function on the power set of n taking values in integers. And the word itself is an abbreviation for integer valued multiset. Multiset is a concept from combinatorics, indicating a system of sets where some of the sets can be repeated. It is modeled by a function on the power set of n, taking values in a non-negative integers. If the value is 0, then it means that set does not belong to the system. If it's more than 0, then it is multiplicity of the set. And we will regard an imset as a vector whose components are integers, are indexed by subsets of n in this way. Actually, any real set function on the power set of n can be interpreted as a vector in the same space. And then we can utilize the topology of this Euclidean space and introduce the scalar product of two vectors of this type by this formula. We will also need some notation for to write formulas for imsets. So this delta sub A is a kind of identifier of a subset A of n. It is vector which has 0 as values with one exception, which is value for the component corresponding to A. Now, this page recalls finally imsets which represent condition independent statements. Given condition independent statement A is independent of B given C, the corresponding semi-elementary imset is an imset which has only 4 non-zero values. Twice plus 1 for A, B, C, and C, and twice minus 1 for AC and BC. Actually, but it is not a really elementary imset. The really elementary imset is that one which corresponds to a triplet where A and B are singletons, like this. The class of elementary imsets will be denoted by alpha. It is easy to see that every semi-elementary imset is a combination of elementary imsets with non-negative integers as coefficients. Here is an example to illustrate this concept. If the number of variables is low, then imset can be visualized in the form of enriched Hasse diagram. This Hasse diagram has ovals which represent the subsets of n, and the corresponding value is written in the oval. So, for example, in case of 3 variables A, B, C, we have this semi-elementary imset which represent the condition independence of A and block BC given empty set. Yeah, and this can be written as a sum of 2 elementary imsets. Now, this page recalls more complicated concept. It is a concept of combinatorial and structural imset. An imset is called combinatorial if it has combination of elementary imsets with non-negative integers as coefficients. Semi-elementary imset is an example of a combinatorial imset. But even more general concept is a structural imset, which is an imset, which means it is a vector whose components are integers, which is a combination of elementary imsets with non-negative rational coefficients. Or equivalently, you can say that one of its multiples by a positive natural number is a combinatorial imset. This is formally defined here. A class of structural imsets will be denoted by S of n. It is evident that every combinatorial imset is structural, and it was an open task for a while whether the converse is true. It is indeed the case for at most 4 variables. Nevertheless, in this paper from 2008, Hemeke, Morton, and Strumfeltz gave an example of a structural imset, which is over 5 variables, which is not combinatorial. Now let me come back to the analogy with graphical models. In graphical context of graphical models, there are certain graphical separation criteria which ascribe formal condition independence model to every graph. An analogy of this is special linear algebraic criterion for structural imset, which is defined here. Given a structural imset U and triplet ABC of pairwise disjoint subset of N, we use this notation and say that the triplet is represented in the imset U. If there is a multiple of U, such that if you subtract the semi-elementary imset representing ABC, then it is a structural imset. In this way, we can define a condition independence model induced by a structural imset, which is collection of all these triplets of pairwise disjoint subsets, which represent valid condition independence statements with respect to U. And then, in analogy with graphs, graphical models, we can say that the probability distribution P, it's Markovian with respect to U, if the condition independence model induced by P contains the condition independence model by U. And in further analogy, we can say that P is perfectly Markovian with respect to U if these models coincide. Here is the main result about the Markovness with respect to the standard imset. It says actually that Markovian condition is equivalent to factorization condition, which is very similar to results in graphical models. And the third equivalent condition, it's some linear algebraic condition concerning the multi-information function. To this, I need to recall the concept of multi-information function. So the multi-information of probability distribution P is formally defined as a Kullback-Leibler divergence of P with respect to the product of its one-dimensional margins. And then if we have finite multi-information, then we can assign to it the multi-information function. This is function, set function on the power set of N, ascribing to any subset A the multi-information of the respective marginal. And we have convention that the value for the empty set is 0. And let me know that if distribution has finite multi-information, then it is marginally continuous. Here is the result. It says if P has distribution with finite multi-information, then 3 conditions are equivalent. The first is Markovness with respect to imset. The second is product formula or factorization formula, where you have the margin densities, and the values of the imset are actually exponents with those margin distributions. So this U plus is positive and U minus is negative part of the imset. And the third condition is the scalar product with the multi-information function is 0. Here is an illustration of the theorem. We again consider the semi-elementary imset representing condition independence of A and block BC given the empty set, which is written here. Then U plus has 2 values, say corresponds to A, B, C and empty set, and U minus has also 2 values corresponding to A and BC. Let me note that the marginal for the empty set is actually constant function taking value 1. Then the theorem says that 3 conditions are equivalent. Condition independent statement, A is independent of BC given the empty set, then the factorization formula, and then some linear equality for the multi-information function. And actually, you see that these 2 conditions actually are the same, like if you state it for a graph. So this imset is a kind of translation of this graph, undirected graph, which has only edge between B and C. So in this context, this is generalization of graphical models. Here is a kind of completeness result for structural imset. It says, once we have a distribution with finite multi-information, then there exists a structural imset such that P is perfectly Markovian with respect to it. In particular, every discrete condition-independent structure and also every regular Gaussian condition-independent structure can faithfully be described by a structural imset. Therefore, in this sense, this linear algebraic method overcomes the limitation of graphical approaches. This is to explain the relation to supermodular function. Let me recall the definition. Supermodular function is a function on the power set of n, so that for each pair of subsets of n, the sum of values for union and intersection is larger than the sum of values for A and B. An equivalent condition is that scalar product with any elementary imset, it's non-negative, or equivalently, any scalar product with any structural imset is non-negative. Let me note in this context that in optimization, you meet often submodular functions which are defined by converse inequalities. Actually, these are -1 multiples of submodular functions. So from a mathematical point of view, there is no difference between these two concepts. Here is a characterization of structural imsets in terms of submodular functions. An imset, that means, let me emphasize that this is a vector with integer components, is structural if and only if it is orthogonally standardized, which means these two conditions, sum of all its values is 0, and for each singleton, sum of values for sets containing that singleton is 0. This is two simple conditions. And then second condition is that scalar product of U with any supermodular function is non-negative. This page is devoted to some inference mechanism between imsets. Let U and V are structural imsets. And we say that U independence implies V if the independence model implied by U is larger than independence model implied by V. And there we have two characterizations of this implication. One is in algebraic terms, in linear algebraic theorem, which says that some multiple of U, if you subtract V, it's a structural imset. And the second condition, it's in terms of supermodular functions. It says that for every supermodular function, if the scalar product with V is positive, then the scalar product with U is positive too. Let me note in this context that there are infinitely many supermodular functions, but if you standardize them, then you get a pointed polyhedral cone. And this cone can be characterized by finitely many generators of its extreme rays. So you can, instead of every supermodular function, you can have every extreme supermodular function here. So therefore, to disprove this implication, it suffices to find an extreme supermodular function such that the scalar product with U it's 0 and scalar product with V it's positive. And you can also translate this implication between imsets to implication between condition-dependent statements. And this leads to some, what I call structural implication between condition-dependent statements. Formal definition is here. Given an input list L of statements and another condition-dependent statement T, then we translate these statements into imsets and sum the semi-elementary imsets corresponding to triplets from L. And then if UL independence implies UT, then we say that L structure implies T and use this notation, which is kind of strengthening notation for probabilistic implication. And this implication is really stronger than probabilistic one. But the point is that this implication can be tested by computational tools. Original expectation is that one needs to characterize extreme supermodular function for this purpose. but this is not the case. Point is that this inference task can be reformulated in the form of LP problem, and then one can use efficient linear programming software packages to test these implications. This is in this paper. In the end of my talk, I would like to say something about application to learning graphical models and about translation graphical models to imsets. The most popular class of graphical models in area of probabilistic reasoning are Bayesian networks. And the main idea here is to translate, represent every Bayesian network structure by a unique vector representative. And this is so-called standard imset. Given a cyclic directed graph, the standard imset for this is given by this formula. Here, this symbol PRG denotes the parent set of the node. And this, if you add I, this is so-called family of the vector. Let me note in this context that there are so-called decomposable graphical models, which are undirected graphical models described by Hodel graphs. And they can be viewed as a subclass of Bayesian networks models. And in this case, the formula to translate them into imset is even simpler. This is to illustrate the formula. Let us consider a graph, a cyclic directed graph over 4 nodes A, B, C, D in this picture. And then this is the formula applied to this graph. This is a term corresponding to A parent set is empty. For B, this is a term corresponding to C, parent set is AB. And then some of the terms cancel each other, and you can rewrite this as a sum of 2 semi-elementary imsets. What we discuss in context of graphical models, we describe often equivalence of graphs. That means they describe the same statistical model. But even stronger concept is concept of independence equivalence, which means that 2 graphs are equivalent if and only if they induce the same independence model. This is typical equivalent to Markov equivalence, which means that they limit the same class of Markovian distributions. Nevertheless, Markov equivalence is context specific. It is relative to a considered distribution framework. That means you have to prescribe your sample spaces. So once your distribution framework is not degenerate, that means some of the individual sample spaces is not degenerate, then these 2 concepts are equivalent. Then the result says that for 2 acyclic directed graphs, we have that they are independence equivalent if and only if they induce the same standard imset. In particular, standard imset is unique representative of the respective Markov equivalence class. Now, let me talk about this structural learning. Most of learning methods in graphical models are based on maximizing a quality criterion. What is it? It is a real function of the graph, an object database, which evaluates how good the graphical model given by G is explained the occurrence of the database. And there are some reasonable assumptions of the criteria. One of them that it should be score equivalent, which means that it assigns the same value to equivalent graphs. The second condition is that it is decomposable. That in context of Bayesian networks means that it factorizes in the same way like distributions factorize according to the graph. And once this is true, then the criterion can be written as an affine function of the standard imset. That means it is a constant minus scalar product of the standard imset with some vector which only depends on database. An important geometric observation is that the set of standard imsets over a fixed set of variables It's a set of vertices, or if you like, extreme points of a certain polytope. So you can potentially apply efficient LP methods to maximize linear or affine function on the polytope. But what you need to this, you need characterize the domain in terms of linear inequalities. So, and this was the topic of research in last decade. For example, it was found that extreme supermodular functions correspond important facet-defining inequalities for these polytopes. And this will be topic of talk by James. And also the last topic was an elegant and challenging conjecture about the complete facet list of for polytope for learning decomposable models. Unfortunately, that conjecture has been disproved recently. That's all. Thank you for your attention.
Thanks very much, Milan. So we've probably got time for one question if anyone would like to ask one. So if you're an attendee, just raise your hands. If you're a panelist, maybe do the same. So I had a very quick question, which is if you just go back to where you were talking about supermodular functions.
Mm-hmm. Should I come back?
Yeah, if you don't mind, just remind myself exactly what I was going to ask.
Here it is. Is this?
Yeah. So this O standardization, is there a way that you can just get that? Can you just take your imset and subtract things? Is that okay? Or
standardization actually means reduction. Yes, it means basically that value of the imset it's determined by sets whose say cardinality is larger than 2. Yeah, so that means value of the singleton it's determined by values of our. So it basically means that actual dimension for in imset it's not 2 over n, but 2 over n minus 1. That's
okay.
What is behind this concept.
All right. Thank you very much.